Hello everyone, my name is Xinyue Zhang from University of Houston. I will present our paper entitled Adaptive Privacy Preserving Deep Learning Algorithms for Medical Data. This is a joint work with Houston Methodist Hospital. And deep learning is fast evolving during the last decade, and it holds great promise in improving healthcare and medicine. Unfortunately, sensitive information, including patient images and electronic health records, can be reconstructed from deep neural networks using attacks during or after the training process. There are several popular types of attacks, such as model inversion attacks, which can reconstruct the training data given only access to the deep neural networks, and membership inference attacks, which aims to find out if a specific data record is in the dataset used to train the deep learning model. Therefore, here comes the question: how to preserve privacy in deep learning? Differential privacy is one of the best solutions since it assures people to learn the characteristic of the whole data, but individual data's privacy is preserved. Now, I will briefly introduce differential privacy. In order not to compromise privacy, I would feel safe to submit a survey if whether I am in the survey, the statistical results should not be changed a lot. Mathematically, it can be represented as there are two query outputs, S and S prime, from the two databases. They are neighboring databases that only differ with one element. We would like to have the distance between S and S prime is at most epsilon, with a probability of 1 minus delta. Here, epsilon is privacy level and delta is the probability of failure. A generic method of achieving epsilon delta differential privacy is Gaussian mechanism that adds Gaussian noise to the output, calibrated to the query function sensitivity. The sensitivity captures the maximum difference of the query function by a single record in the worst case. A smaller sensitivity means less distortion, and smaller epsilon means better privacy. There are various flavors of differential privacy. The differences between them come down to how to characterize the privacy loss. In this work, we adopt TCDP since it can provide sharper and tighter analysis on the privacy loss for multiple iterative computations compared to the epsilon delta DP. And in order to preserve privacy of the training data, during the training procedure, the differentially private noise is supposed to add to the gradient in each iteration. When calculating how much noise needs to be added into the gradient, it is supposed to have the sensitivity of the gradient, which is difficult to quantify. Therefore, we control the sensitivity by clipping the gradient in L2 norm. In order to increase the accuracy, it is intended to add smaller and smaller noise to the gradients through the training. Therefore, we propose to inject linear decaying Gaussian noise to the gradient during the training. The overall privacy budget can be calculated with the equations on the right. We demonstrate the experimental results of the proposed scheme on one medical dataset, Chexpert, and two popular image datasets, MNIST and Sepharton. We can observe that our proposed adaptive DP model outperforms the DPSGD model, which adding the same amount of noise to the gradient during each iteration. We also demonstrate the impact of different parameter settings of the proposed private deep learning model. With a larger noise decay rate or a lower clipping threshold, it costs less privacy budget during each iteration. Therefore, the model performance is better since we can achieve more epochs during training. And now I will draw the conclusion. Privacy preserving in deep learning is extremely important, especially in the healthcare and medicine field. So we propose to inject linearly decaying Gaussian noise into the gradient during the training. We adopt TCDP, which can provide a simple, explicit, and tight privacy bound analysis. We validate the effectiveness of the proposed approach with a real-world chest radiograph dataset. And that's all. Thank you.